All right, today what we're going to look at is the idea of the tangent line problem and how that is connected to what the kind of core idea behind calculus, which is a derivative. So the first thing that we're going to do is I'm going to actually let you do some of this and we'll kind of work together. Is first I'd like you to sketch the function f of x equal to 3x minus x squared. And I want you to kind of think about what's happening to the graph at x equals 1. What I'm really talking about here is this idea of how fast is the graph changing at this point. And this is kind of bring into kind of our idea that we want to look at what is an instantaneous rate of change, or an instantaneous velocity of how fast the graph is changing at that instant, at that single value that we are looking at. And of course, that was a very difficult quantity to calculate because how do you calculate rate of change in y over change in x, when you only have one single point? And so the idea is what are we talking about with the slope at this point? So I want you to think about these questions here in part A, and I'm going to pause the video for a moment, and then we'll come back and we'll talk about them. All right, coming back together, the first thing, this is all a review of pre-calculus and algebra 2, is we have a quadratic. I factored my quadratic and set it equal to 0, found my two x-intercepts, 0 and 3. I know that the vertex occurs exactly halfway in between 0 and 3, so at 3 halves. And then to find the y-coordinate of the vertex, which is always going to be important, I plugged 3 halves into the function, and I got 9/4. An alternate method, if you'll remember, here's your shortcut formula for your vertex. And that shortcut is, if you have your parabola in ax squared plus bx plus c form, the x-coordinate of the vertex is always negative b over 2a, and then I just basically plug them in from over here. My b was 3, my a was negative 1, and so I need a negative right there. Oops, I should have noticed that that was a negative mistake, which would make this over negative 2, which is 3 halves. Okay, and then I'm determining what's happening to the graph at x equal to 1. I also came over here, plugged 1 into the function, got the point 1, 2. So we're talking right here at x equal to 1 at the point 1, 2. And we want to know what the slope is at that point. Well, what exactly are we talking about? If we're talking about the slope at that point, we're talking about the slope of the tangent line. So I'm going to go ahead and draw my tangent line now. I'm just going to extend it up here. And so we'll talk about this. I'm going to say the slope of the tangent line is going to be what we're going to consider to be the slope at that point. That slope of the tangent line is going to be what we're going to be using as our instantaneous rate of change. If I can calculate the slope of the tangent line, then I can calculate the instantaneous rate of change at that point. Okay? So now we're going to come down here to B, and we say, well, now draw a secant line between the points 1, f of 1, which is my point right here at 1, 2, and the point 1 plus h, f of 1 plus h. So we're going to basically move over just a little bit. Doesn't really matter where at this point. I'm going to move over a distance of h. That will put me about here, and you could actually have that anywhere. I'm just going to go ahead and put it at this location for myself. And that would be the point right here. Its coordinates would be 1 plus h and f of 1 plus h. And then I'm going to draw a secant line in between those 2 points. Now, obviously, when we're taking a look at this secant line, the very first question I'm going to ask is that a good estimate of the slope of the tangent line? Not really. So the idea is that that's not a great estimate. I'm going to get a better estimate shortly. First, though, let's go over here and continue with what B is. They want to compute the slope of that secant line, because that's going to be skill number 1. So the slope of your secant line, which of course is your change in y over your change in x. For this problem, your y-coordinate over here is f of 1 plus h, and your y-coordinate for this point was 2, which was really f of 1, we'll go ahead and leave it there, all over our 1 plus h minus the x-coordinate here, 1. I'm going to simplify a little bit, f of 1 plus h minus 2 all over h. So that would be a formula for the slope of the secant line. And basically all I need to know is I need to know what h is, plug it in, and then that'll give me the formula for the slope of the secant line. Now the slope of the secant line, that is a rate of change. However, it's not the instantaneous rate of change. It's what we're going to be calling the average rate of change. Oops. Now, on average, you are going at whatever the slope is. Now, of course, this looks almost close to 0, but was that the speed that the graph is changing throughout? No, it's obviously going to be moving at a positive rate of change at every point over here, and then a negative rate of change here, which is going to cause it to decrease. But the average between 1 and 1 plus h, the average rate of change on the interval 1 to 1 plus h. That's what we're basically looking at, the slope of the secant line. Now what I want to do is I want to be able to use this slope of the secant line to find the slope of the tangent line and ask the question of how can we do that? Well, if I come in here and what if I start letting this point right here move along the curve closer to the point 1, 2. So we'll move it here, we'll move it a little closer, maybe a little bit closer. And as I do that, if I draw those secant lines in, even though this is not a great estimate of the slope of the tangent line over here, as I start adding in more and more secant lines, and I'll let the points get closer and closer, I'll add that one in, let's see, I'll add this one in. What's happening each time I add another one in? Each time I get closer and closer and closer, as the point moves closer, the secant line becomes a very good estimate of the slope of the tangent line. Now the question is, what am I basically doing there? What kind of a process is that? That's what we call a limiting process, and this is where calculus comes into play. The idea that we're going to take the limit, and what's happening here, what am I basically doing? As this point moves closer, what's happening to the location of this x value on the x-axis? As it moves closer and closer and closer, what happens to h? H is going to go to 0. So we're going to take the limit as h goes to 0 of this slope formula that we have, of our f of 1 plus h minus f of 1 all over h. And as I calculate that, the slopes of the secant lines, the closer and closer that you get to the point 1, 2, that is going to be an estimate or a way to find the instantaneous rate of change. So this is kind of our answer to C right here. This is our formula that we would use to find the slope of the tangent line at x equal to 1. Okay? And so basically what we're noticing here, we'll come back and actually calculate this for practice, but what do you notice is happening to the secant line as h, the distance between your two x values of the 2 points, as your, basically h is your delta x. Your delta x is going to 0 the closer the two x values get to each other. So as h goes to 0, do you see that that's the limiting process for our finding the slope of the tangent line? We can't calculate it directly, but we can look at the limit as h goes to 0 and find out what that is. All right, now I'm going to pause it, and I'm going to let you, for this function, actually go ahead and calculate what this limit is. Let's actually find the slope of the tangent line, or the instantaneous rate of change at x equal to 1. You might need your own paper. Obviously didn't leave enough space here. I'm going to say see next page, and I'm going to pause it right here and let you go ahead and calculate this using our practice with limits. Okay, just wanted to come to the next page just to make sure you have the idea of what you're working on. I know that you've paused it, but we have our function. We're trying to find the instantaneous rate of change of f of x at x equal to 1, which is also known as finding the slope of the tangent line to f of x at x equal to 1. All right, so I'm going to pause it again and let you finish, then hit play, and you'll be ready to go and see your answer for this. Okay, so you can check your answer here. Basically, I plugged 1 plus h into the function rule everywhere there was an x. I plugged in 1, got the 2. I did a little bit of algebra here, distributed, FOILed that out. Don't forget to distribute your negative. Collected like terms, canceled what I could cancel, factored, removed the discontinuity, and then once I remove the discontinuity, I can use direct substitution, plug in, and get my slope of the tangent line is 1. Now, if we take a look at this picture, does that seem pretty reasonable for our tangent line slope? If you recall, that's that one, and I'm going to make that a blue color so it stands out. Does that look about right, that I'm going, here it goes through here, up 1 over 1? Okay, not bad, given the fact that we're sketching it here on our paper. Now, a couple of things that I want to add to this at this point. Let's talk about some notation. So this is basically what we're calling the slope of the tangent line, what this formula is going to find for us. Okay? All right, so this is going to be our formula for the slope of the tangent line to f of x, to your function, at x equal to 1. Now we're going to give that a name, and the name that we're going to call this, and kind of what basically over half of calculus that we're going to be studying this year is going to be looking at, this is called the derivative of f of x at x equal to 1. So that's going to be kind of the first thing. These all mean exactly the same thing, just different terminology that we're going to be using. This is also known as the instantaneous rate of change on your function f of x at x equal to 1. Okay, so 3 different things, all talking about the same thing. Now we need some notation for this as well. We'd like to kind of give this a name that we can talk about. And the name that we're going to actually bring in here, we're going to start calling this f prime of 1. So what we're looking at here is this notation. The reason you have f is because you got to know what function you're on. This prime is what's telling you that this is a derivative, or the slope. And of course your input is telling you that it's f prime of 1. It's the slope of the tangent line at x equal to 1. And when you see this on your paper, you do read as f prime of x equals to 1. F prime of 1. And then basically you know that this, and this all mean exactly the same thing. A little bit later we'll kind of bring in another few notations for this, but for right now, that's the one that we want to get used to using. Alright, so now that we've talked about this and we've kind of had this idea for this example, we're going to come down here to example 2. Now, one thing that we want to do is this example that I did here, I found the slope at x equal to 1, and only x equal to 1. If I move to a different x point, if I move over here to maybe x equal to 2, whatever that value is right there, then I need to, obviously it's going to have a different slope. So I have to redo this problem all over again. But instead of that, what I'm going to do is I'm going to use a similar method, except now I'm not going to actually pick a point like 1, f of 1. I'm going to leave it general and leave it as x, f of x. So on our little function that we're dealing with, I'm just going to do a quick, simple sketch here. We're going to have our point here, and I'm just going to call it in general x, f of x. I'm going to move over a certain amount of points over to here. So this is x. This will be x plus h, that distance that you move over. And so the coordinates of that point would be x plus h, f of x plus h. So what we're basically going to do is we're going to use this idea on the function, but come up with a general formula. It's going to be a formula for the derivative where your input is going to be an x value from the graph, and your output is going to be the slope of the tangent at x. So essentially all we're going to do is we're going to use our limit definition, the limit as h goes to 0, and we're going to, instead of doing f of 1 plus h, which is what we did above, we're going to leave it as x plus h, minus, instead of f of 1, we're going to do f of x. We're going to keep this general all over h. Now what this will do is it will find a general formula for our derivative at any point x. So it'll be f prime of x. Now for this problem, we'll just run through it real quick. We have the limit as h goes to 0 of our 3 times x plus h minus our x plus h squared minus f of x, that's minus the entire formula. You can put parentheses and distribute in the next step, or we can just go ahead and subtract each of the items. So it'd be minus 3x plus x squared all over h. Now we have to do a little algebra. Limit as h goes to 0. This would be 3x plus 3h minus, I'm going to go ahead and just FOIL this and distribute the negative at the same time. So we'd have minus x squared minus 2xh minus h squared. Bring down the rest of our terms. Once I get it all multiplied out, I run that sledgehammer here. I'm going to look for things that cancel. 3x and minus x squared minus x squared. Notice everything that's left has an h in it. So I'm going to go ahead and pull that out. And by this time, this should be pretty much old hat to everybody in terms of our practice. So h. I'm left with 3 minus 2x minus h. The reason that we factored it out was so that we could remove the discontinuity that's causing the problem. And once I remove the discontinuity, now I can plug in. Now be careful, I'm plugging h in for, or 0 in for h, not for x. This is the limit as h goes to 0. In this problem, the x and the 3, they're constant. They don't have anything to do with the variable that I'm looking at. So this would end up being 3 minus 2x minus 0, which of course is just 3 minus 2x. So what we've come up with now is that we have a formula that our derivative, the slope of the tangent line at, and I'm going to underline the word any point x on the function f of x, which in our notation, f prime of x is going to be 3 minus 2x. Okay? And that kind of gives us our idea. That is a general formula. Now, if I wanted to calculate some of these slopes, I can use the formula. I don't have to redo it every time. We did above f prime of 1. Well, plug in 1. 3 minus 2 times 1, that's going to give us a 1. That's the slope that we found earlier. You input an x value. Your output is the slope of the tangent line. Let's do f prime of 2. F prime of 2, 3 minus 2 times 2, or negative 1. Now, does that kind of make sense to us? If you think about where we are, here's our point 1, 2. Now, if I'd drawn this very nicely, 2 should also have a coordinate of 2. Should have the same height because it's equidistant on the other side of the vertex, and it's going in the opposite direction. So, of course, it would have the opposite slope that you're looking at. What if I did f prime of the vertex value 3 halves? What do you think the slope of the tangent line at the vertex would be? Right, we can plug it into our formula, 3 halves. That's going to be 3 minus 3. Oh, that's 0. Does that make sense that we have a horizontal tangent line here? If I look back at my picture, right here would be where the vertex is, and that's a horizontal tangent line, of which the slope would be equal to 0. That's going to be a very important fact coming up here very shortly. All right, and then the last thing kind of on this page that we're looking at, why did I have this little comment? Listen closely and you can hear Galileo grumbling in his grave. This is what Galileo was trying to do. He was looking at the orbits of the planets, and he was trying to determine how fast they were moving at any given instant. And he had a lot of difficulty with this. But what we've basically done is we've come up with a way or a method that can allow us to find instantaneous rate of change, which is what he was trying to spend his life's work actually doing. The two mathematicians that are responsible for this are Newton and good old Isaac Newton, a very brilliant mathematician, and Leibniz. Newton and Leibniz, when you take a look at this, there's a big feud between these two about who gets credit for calculus. Now, to be honest, I'm not going to get a lot into that in this set of notes. Newton and Leibniz kind of had the same ideas about the same time. We're actually using Leibniz's notation. This limiting process is more of a something that Leibniz came up with. Newton used something called a fluxion, which is this idea of infinitesimally small values, which is a similar thing to a limit. But what happened is they kind of fought back and forth. It went to the royal, I don't know if it was a royal board, I have to look up and see what the actual name of it is. It actually went before the kings and the queens of the time because they were fighting about who would actually get credit and who wrote it up first. And, you know, so right now, well, Newton kind of won, but that's mostly because he had connections, not necessarily because his work was any better than Leibniz's work. But they're both considered really the founders of calculus. All right, so let's take a look over here at the next page. So this is kind of just recapping what we just talked about. And what that's going to say is that we've now found a slope function. A function where we input an x and the output is the slope of the tangent line. This is going to be called the derivative of f of x. Our notation for it is going to be f prime of x. And we can find the slope of the tangent line at any point. Also known as the instantaneous rate of change. Now, the next thing, and we're going to spend a lot of time talking about this, is if a point has a tangent line and the slope, and it has a slope of the tangent line, if that slope exists, then the function has a derivative. It is said to be differentiable. If it has a slope everywhere, then the entire function is differentiable, but we'll also talk about differentiability at a point and some cases where we would be interested in when it doesn't have a derivative and when it does. But the big thing is here's our limit definition of the derivative of a function, that we can find a general formula for the slope by simply doing the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, so let's come down here. We have example number 3. And again, the idea is that this is going to give you a variable function that can be used and reused for different x values. So for example, here's my nice derivative or function f of x. I want to find a derivative function because here in part B, what I'm going to do is I want to find the slope at -1, 0, and 6. I don't want to do 3 different problems like I did in the previous page. Find f prime of -1, f prime of 0, f prime of 6, and do the limit process 3 times. What I want to do is the limit process once, using it as a general idea and come up with a formula. So I'm going to pause it. I'm going to let you work through this and then come back together. Now, when you get to here, let's do A and B first and then come back together. Because I want to talk about C, finding the equation of the tangent line kind of separately. All right, so I'm going to pause it. Go ahead and work A and B, and then we'll come back and we'll check and see what you have found out about the slopes at -1, 0, and 6. All right, let's take a look and check your value for your derivatives at -1, 0, and 6. Here was my limit definition of the derivative. We plugged in x plus h into our function, subtracted the function over h, did a little algebra, sledgehammer, combine like terms, cancel what you can cancel. Okay, everything that's left has an h in it. We pull the h out, remove the discontinuity, which allows us to use direct substitution, gets us to here. Here's our formula for our derivative. So f prime of x is 4x minus 16. Then from there, plug and chug, plug in -1, plug in 0, plug in 6. And what does this tell us about the derivative? That the function itself, if you have a negative sloped tangent line, the function must be on a decreasing section. So at -1 and 0, the function must actually be decreasing at those points. And it must be increasing at 8 because it has a positive rate of change. All right? Now, I'm going to actually go over, because obviously I've used all my space, and I actually want you to take some notes. I want to talk about a little bit of a review about the equation of lines here before I do part C. So let's add, kind of take out your own paper and let's add this in to make sure that we have a good understanding of our linear functions that we're going to look at. I'm going to remind you there are several forms of lines when we're looking for equations. We have our point slope form. And I want you to put a big star by this one, because this is the form of a line that is actually most preferable and actually the least work. On AP, you want to be making sure that whatever you do, it takes the least amount of time. And what you want to think about here in point and slope formula, let's remind ourselves what this is. Usually it's y minus y1 equals mx minus x1. You have that as our idea that the m right here is going to be our slope, which you're going to plug in a slope value. And then you have your x1 and your y1, kind of come down here. X1 and Y1 are going to be your point. So it's some point that you have that you're going to plug in the values for. Now, in general, a lot of times we like to have our equation solved for Y. So what we're basically going to do, and in most of the time, okay, so usually we like to have it solved for Y. So all I'm going to do is simply move this minus Y1 over to the other side. So it's mx minus x1 plus y1. Notice I'm not multiplying it out. I'm just going to put it in a form so that it's in y equal form, but yet it is still very easy and very quick for us to work with. And this is going to be the preference when we are doing it, because there's going to be no work. You simply plug in your slope, and just as a reminder in what we're doing right now, this is your f prime of c, whatever point that you're, or whatever slope you're looking at, the slope of the tangent line. And then right here, your x1 and your y1, if we're thinking about where those are coming from, x1, that's your c value. And then to find the y value, that's f of c. So we're going to essentially be given these pieces of information when we find the derivative. And so all we have to do is plug them in. So for the example that we're looking at, I believe on this one it's asking you to find the equation of the tangent line. Okay, find equation of the tangent line at x equal to -1. Okay, now let's put down, just bringing back what we had from the previous page. We already know f prime of -1. We calculated that in part B, that's equal to -20. So essentially what we did by calculating the derivative is this is the slope of the tangent line. Okay? Then I go, well, what point? I need a point in order to do point-slope form of a line. Well, I know the x-coordinate of the point is -1. And then to find the y-coordinate, I do f of -1. So for this function, okay, remind you your function was the f of x equal to 2x squared minus 16x plus 35. So to find the y value, when you have an x of -1, I simply plug this in. And if I plug this in, my y value, this would be 2 minus 16, actually plus 16, so 2 plus 16 plus 35, which is going to give me, I think, a grand total of 53. So right there, I have the slope and I have a point that the tangent line goes through. So the equation of the tangent line is going to be y equals my slope, -20, x minus -1, which becomes +1, and then plus 53. And then you're going to walk away, because there is nothing that says you need to simplify, put this in slope-intercept form, or anything. If you are on a free response question, you're done at this point. You have the equation of a line. You don't want to do extra work in a problem and then maybe make a careless mistake that you didn't have to make, because you're done right there. So you're just going to walk away. Now I do want to talk about, however, the other two forms of a line that you're going to see. And this is mostly from this point on, is only if you're in the multiple choice section. And that is when you look at your answer responses that are in choice A, B, C, and D, is if it's in slope-intercept form or in general form, you have to be able to get it from this to those to recognize they're the same thing. All right, so let's talk about slope-intercept form. All right, in slope-intercept form, that's, if you recall, your y equals mx plus b. Well, yeah, we could go back and do this whole thing about plugging in a point and finding b, but if you already have this, really to get it in slope-intercept form, all you have to do is distribute your -20 and then combine like terms. So from up here, I can just look at it and go, for this problem, it'll be y equals -20x, and then I have -20 and then plus the 53, which would be simply plus 33. So even getting this, going to that would be fine. Then you would look for the multiple choice that has this as a selection. The second thing that you're going to see in your multiple choice, the other form of a line, is going to be what we call the general form. When we look at the general form of a line, that is ax plus by equals c, and that is where all of these parameters, a, b, and c, are going to be integers. And so for this problem, essentially once I'm over here, well, what am I going to do? We'll just put the x's and the y's on one side, the number on the other. So we end up with 20x plus y equals 33. And so you would look through your answer choices and choose whatever would look like this. Now, just as a comment, you do realize that this, and if an answer choice is this, that those are exactly the same thing. So if you don't see your answer choice, just say, oh, if I multiply both sides by negative, that's equivalent. So you look for that. You pretty much are only going to use slope-intercept and general form when you are in the multiple choice section. Any other time, you are going to go with this point-slope form of a line, get it to this, and then leave it there and walk away. All right, now coming back, let's just kind of lay out all the meanings and distinctions between all of our formulas and things that we've been talking about. Now, typically, over here is going to be where we're talking about the secant line. And in the secant line, what you're basically saying is that if I want to find the slope of the secant line, I really need 2 points. So notice I'm doing specifically a f of a and b f of b. So all of the following things are equivalent. If I say the slope of the secant line, change in y over change in x, f of b minus f of a over b minus a, and this is also known as the average rate of change on the interval from a to b. And these are all specific values. You will find a number for this when you are plugging it in. Over here, if I want to use 1 point, this is where we start talking about the tangent line instead of the secant line. And technically for all of these, I'm talking about what about each of these? I'm talking about the tangent line slope, and I'm talking about, or secant line slope, and the tangent line slope. But I only have 1 point. Well, that's okay, as long as I use this idea of the definition of a derivative, I can plug in the specific value here and here, and actually calculate what that slope is. This is what we did over in the beginning of the notes on the first problem. Where I did not get a specific formula, I basically found the actual value of the slope at a specific point. This is what we call the modified form of the derivative. Modified form. Okay? And this will come up a little bit later and we'll be using it. Anytime you only need to find one slope, this is always the fastest thing to do. This is also known as, in our notation, f prime of c. It's the derivative at x equal to c, and it's the instantaneous rate of change at x equal to c. Now, of course, on these two, you really should say on f of x so that we know what function that we're talking about. And of course, those are different. If I was actually talking about a formula, the general formulas, kind of add this here on the bottom, the general formula for the slope of the secant line is going to be, all right, so the general formula over here, if I just want to find the slope given a point x f of x, you would be doing your f of x plus h minus f of x all over h. And that would be what we consider the difference quotient, which is going to be the formula to find the slope at any point x. And you need an h because you've got to have 2 points. So you have x, the point you're at, and x plus h. But to turn it into the derivative, the slope of the tangent line at any point, we add on this limit as h goes to 0. We put in the limiting process, which is the calculus part of this, and we then calculate a general formula by calculating this limit. And so this would be f prime of x, and we don't really have a name or notation for this. We just say this would be the slope of the secant in general, and it's what we call the difference quotient. Okay, so coming over to here, I'm going to let you try this example 4 as homework. Part of the reason why I'm giving you this example is that what I want you to do is to get used to not just using x and f of x. So right now notice that you're using t and g of t. So what I first want you to do is write the definition of the derivative as a limit using the letters in the problem. That's important for AP. You have to use the same letters that they give you in the problem. So I'm going to pause it. What I want you to do is write your definition of the derivative, and then I want you to find the derivative function g prime of t. I'm actually going to pause, give you a couple seconds, and then I'm going to write just the first part of it, and then I'll pause it again. All right, just to make sure you're started off in the correct notation, notice that I'm doing g prime of t now. So finding the derivative on the function g for any t value that I put in. We're going to take the limit as h goes to 0, and it's g of t plus h minus g of t over h instead of f of x plus h minus f of x over h. We're just translating it. And then we're plugging it into here. Now I'm going to pause it again, but I will remind you what method, what technique is the technique that we're using algebraically to calculate this limit. Our technique is to multiply by the LCM over LCM, the least common multiple. So I'm going to let you plug and chug with your algebraic technique for finding this limit. I'm going to pause it, come back together, and we'll check your answer. All right, coming back together, we have applied our multiply by the LCM, and since these have no common factors, this and this are two completely separate factors, that your LCM is simply the product of the two. When you multiply, make sure that you are distributing, so you distribute the numerator to the numerator. You cancel the common factors, and I'm left with t plus h, t plus 1. I multiply through here, the t plus 1 cancels with the top, and I'm left with t times t plus h plus 1. The bottom, don't multiply it out. Remember, your objective is to remove common factors, and this is already factored. So you would never in any way multiply that out. Do not spend your time multiplying that out. However, on the top is not factored. So I'm going to have to now sledgehammer the top, distribute and FOIL here, distribute here, collect like terms. I'm left with an h. Oh, look, common factor goes away. Remove the discontinuity. Now I can plug in 0 right here for the h. So we basically let the h go to 0, and I'm left with t plus 1 times t plus 1, or t plus 1 squared. So that gives me a formula for the derivative at any t that I want. All right, now the second part of this problem says that once I have the derivative function, I want to find the equation of the normal line. Now let's kind of come up here and let's define what a normal line is. If I have a function, just any generic function at all, and I'm looking at the tangent line slope. So suppose we look at the tangent line right here. The normal line is simply going to be defined as a line that is perpendicular to the tangent line. Okay? Now, do we remember what's true about perpendicular lines? The slope of the perpendicular line is going to be the opposite reciprocal of the slope of the tangent line in this problem, because they are the opposite reciprocals. So the slope of the perpendicular, which is going to be the normal line, is the opposite reciprocal of the slope of the tangent. So when I start talking about the slope of the normal line, well, I'm simply going to do negative 1 over if I'm doing f of x, then it would be f prime of x, but in this problem, it would be negative 1 over g prime, and I'm doing it at t equal to 1, so we would do g prime of 1. So I find the slope on g, slope of the tangent line at 1, and then I do the opposite reciprocal of it, and that will give me the slope of the normal line at t equal to 1. All right, so let's come over here and let's do that together. All right, so now just remind yourself that when you're looking at it, I want to find the equation of the normal line. I need a slope. So my slope is going to be, I'm just bringing it down from above, negative 1 over g prime of 1. Okay, and this is the slope of the normal line. Get into the habit of labeling things when you're looking at it. Well, what is g prime of 1? G prime of 1, I plug in 1 down here. 1 plus 1 is 2, 2 squared, so this would be 1/4. So my slope of the tangent line at 1 is 1/4, so the slope of the normal line is -4. Now what point are we going to use? Okay, if you take a look back up at our picture, isn't it, it goes to the same point that we had earlier. So our point was C, f of C, which in this case would be 1, f of 1, except I'm not on f. What am I really on? I'm on G. So I need to do 1 G of 1 to find the point. All right, I plug it in, go back to the original function, which I'll slide over. If I plug in a 1 there and a 1 there, 1 over 1 plus 1 would be 1/2. And then I simply write the equation of the normal line, y equals -4 slope, x minus 1 plus 1/2. And that's the equation of the normal line at, now what did I do wrong when I put that x in there? See, that's going to be the thing that's going to be hard about the AP, is because that you're so used to doing x that you keep adding it in, but you have to remember, what variable am I using? I'm using t, so you make sure you put your t in. So at t equal to 1. All right, and then of course if they ask you for the equation of the tangent line, what would it be? It's essentially the same thing. The only difference is instead of -4, you would have 1/4, t minus 1 plus 1/2, and that would be the equation of the tangent line at t equal to 1. So depending on what they ask you for, you should be able to do that. All right, so I'm going to stop this set of notes as part 1 here. I think that's a good overview of both what a derivative is and finding the general formula for the derivative using the limit definition, and finding the equation of the tangent line, finding the equation of the normal line. We'll come back in the next set of notes and we'll start looking at some applications. This idea of instantaneous velocity and instantaneous acceleration. So we'll make that for the next part of the video notes.